right. So we're going to continue to finish up lecture 2 with a few basic definitions and then discuss about DSeparation, which is sort of the most rigorous and easiest way to check independence relations on directed and undirected graphs. So let's pick up a few slides from lecture 2. So this is an example, but I mean, I hope, you know, it takes 10 minutes for somebody to type this equation, right? Which means I expect you to at least spend 10 minutes to actually read it, okay? And it looks sort of everything trivial, but there is a lot of substantive sort of calculations that are going to carry on everywhere in the course. So I wanted to go through this example in a few more details, maybe, you know, spend a minute or two. So this marked nodes, these largest nodes x2 and x3 indicate, and this will always be the case in the course, indicate evidence. So the idea here is we have observed x2 and x3, that's why they're marked, okay? And what we want to prove is if we have observed x2 and x3, x1 and x6 are independent. Okay, so this is what the notation means. So again, x2 and x3, I marked them, so I got some evidence, and I want to know now, given this evidence, are x1 and x6 independent? Okay? So effectively, what we need to prove is, so we need x2 and x3 given, so we need to prove that the probability of x6 given x1 and x2 and x3 is equal to the probability of x6 given x2 and x3. In other words, knowing this evidence, the information of x1 doesn't tell me anything new about x6. Okay? And obviously these proofs are the long way, but this is where we are at the course at this point. Okay? So what I have done is I wrote this as the joint in the numerator is the joint probability of x1, x2, x3, and x6, which means this is the total joint probability factorized on the graph, and then obviously I have to integrate out x4 and x5, all right? And then in the denominator I have the join of x1, x2, and x3, which means I have to integrate out x4, x5, and x6, okay? The important thing that algorithmically is going to save us when we work with this type of graphs is that we can push some of these summations inwards. So for example, you have summation in x5, and the only term that depends really on x5 are those two last terms, so you can push x5, the summation, at this point, okay? And then there's a summation in x4. These terms don't depend on x4, so you can push the summation in here. But notice there is an x2 there, right? And that will be part of the summation that I perform in x5, all right? So the summation is first in x5, then in x4. And similarly in the denominator is the summation in x6, then in x5, then in x4. It's important to, this is sort of the main trick used to allow rapid inference basically into probabilistic graphical models. If we had to perform all summations at the same time, good luck. Okay? All right. So a lot of the things cancel out. So this, because this is a conditional distribution, this summation, it comes equal to 1 regardless of what x2 is. So this and this cancel out. So basically, I'm sorry, this doesn't cancel out. This is equal to 1. This is equal to 1. So basically, this and this cancel out. This and this, you know, it's 1 anyways. So I get this big summation on the numerator, which is this. And then, as somebody pointed to me yesterday when he came to see me, he says to me, why is this equal to that? Because you notice suddenly, I plug in addition to x3 and x2, and in addition to x2 and x5, I plug in an x3. Why is that? So here I have x5 given x3, all right, x5 given x3, and then I put that this is equal to x5 given x3 and x2. What property from the ones we stated? Parent no, I don't see a parent. X2 is not a parent. Yeah, but one of the fundamental independent properties that we stated, and we will see 3 times today or 4, is that given the parents, the node is independent of the non-descendants. Okay, and the non-descendants are the ancestors basically, plus some extra nodes. Okay, so in this case, X2 is not an ancestor, is a non-descendant, because the only ancestor of X5 is X3 and X1. All right? X2 is a non-descendant. So in other ways, you can see the arrows. You can go from 5 to 6. You cannot go to 2. So X2 is a non-descendant. Okay? So again, we will see this property together. But given the parent X3, this the probability of X5 is independent. X5 is independent of the non-descendant X2. And similarly, on the second probability, I plug in what I have here 3. So given X2 and X5, 2 and 5, which are the parents of X6, I plug in 3, and 3 is a what? It's it's obviously non-descendant, but it's it's a grandparent basically of X6. Okay, it's an ancestor of X6. Okay, so and the reason I have to plug in this times that is because these 2 distributions together, they give me the probability of X5 and X6, condition X2 and X3. And if I integrate X5 out, I get the probability of X6 given X2 and X3. And then this identity has been proved. Okay? So basically what you see here at work is a lot of little things that are important basically when you work with high dimensional distributions. So obviously, we use the factorization of this distribution on the graph. We managed to do some of the marginalizations by appropriately moving the summations inwards, okay? Starting basically from the leaves and then eventually going to the root as needed. And then we use the independence relations here of the parents of a node being given the parents being independent non-descendants, and that's it. Okay, so let me we discussed this example, but I want to go back to it, and then we will do this with again with the DSeparation algorithm. So we have a case here of a wet grass, sprinkler being on or off, rain on or off. So basically these are binary variables, okay? And you can see various problems. One that goes from causes to effects. So if it is cloudy, this will cause rain, and this will cause, let's say, the grass to be wet. So and a forward inference problem can be, is the grass wet given that it's cloudy? Right, so information propagates in the direction of the graph. All right, so this is from causes to effects. And that's the easy problem. All right, so that's a very easy problem. This is very similar sort of to what you do in Bayesian statistics with the likelihood, right? If you know the parameters, what is the output. So here, this causes the grass to be wet, so you're asking what is the probability of W equal 1 given that C equal to 1. A more important problem is the inverse problem, to go from effects to causes. So if the grass is wet, somebody can say, is it raining? In other words, if W is equal to 1, is R equal to 1? What's the probability of that? Or even more important questions, if the grass is wet, is the probability that it rained higher than the probability that the sprinkler is on? Okay? Well, actually, that's a little bit different problem from the one I have here, but basically it's in the same spirit. And something that we will see in more detail in the lecture today is what happened, is this inequality. So let's look at it again carefully because we went through it, but you know, I want you to start getting this even if you see it 10 times in the slides. So I have two conditional probabilities. Both of them say are conditional on the grass being wet, W equal to 1. And what I trying to infer is if the sprinkler is on or off. And the argument here, if this equation is correct, I say, given that W is equal to 1, I say that if I also know that it rained, this probability is less than that. All right? So I want you to look at this equation carefully because both the sprinkler and the rain, they cause the grass to be wet. So if somehow, so with this as an evidence, if you have some information that it rained, this immediately reduces the probability that the sprinkler is on because this evidence explains that the grass is wet. Right? So you have two possible causes here that the grass is wet, and if this was not there at all, right? So if we didn't have any, the lower part of the graph is the probability of the sprinkler, is the sprinkler and the rain independent of each other. If there is no connections to anything, you just have the sprinkler and the rain, are they independent? All right, if they're independent, now once you observe the grass, all right, that's not the case anymore. They're not independent, right, because knowing that something about if it rained or not immediately tells you something about if the sprinkler is on or off. So this is a weird event, but it only appears in directional graphs, and it is goes with very many names. Explaining away is the most common sense name, right? So observing one of the causes that the grass is wet, it explains away the fact that the sprinkler is on. Okay? Sort of a concept that doesn't come in other sorts of graphs like undirected graphs. Okay. I basically have some of these calculations. You can work them out, okay? And the same way as the first example that I showed you today. So using these marginalizations and moving the summation inwards to do the calculations efficiently. So I'm not going to repeat this example. So the local property, the Markov property that we have used, and I will try to give you versions, different versions of this, is that given the parents of a node V, xv is independent of the non-descendants of the node V. And I am generalizing here. I'm not saying of the parents of the, I mean, I'm not saying of the ancestors of the, I'm saying the non-descendants. Which set is bigger, the ancestors or the non-descendants? Which set is bigger? The ancestors or the non-descendants? The non-descendants is bigger, right? So I can write this also. I can take a subset of NV, which are the ancestors, and say xv is independent of the ancestors given the parents. And I want you to think, if you have a topological ordering, the ancestors basically are the nodes that are numbered before V in that order. But the non-descendants, they have numbers that are higher than V. Right, it's important here. The non-descendants have numbers that are higher than V. Okay. So obviously in this case, for this example, let's say this is some test of a student that gets different grades and some results of a DSAT thing. So let's accept this graph like that, so we don't have to discuss all the details, but basically the parents of this are this no difficulty and intelligence, but you notice also SAT is a non-descendant, right? So given B and I, this node is independent of SAT, okay? But notice something that I am discussing on the bottom that if you look at the grade, given the intelligence and the difficulty, all right, it's not independent of the letter, all right, because this is not in the list of the non-descendants, okay? So G is not independent of L given I and B. All right. A little bit about inference, and again we discuss it very fast, and we will spend at least 2 lectures to discuss inference later on. So right now, accept this as an introduction to the topic, not that we cover anything. For those who know about hidden Markov models, and I think we saw in lecture 1, where you have a hidden state and we have some noisy, let's say, observations. Maybe the problem is to estimate the state given the observations. But also, you know, when we say inference, not only do you try to say something about non-observed variables, but maybe there are lots of parameters, static parameters in the model. For example, when you say, you know, you decompose the joint probability distribution in conditionals, do you know those conditionals? Do you know the probability of x2 given x1? Maybe you have some parametric definition, right? You say, this is defined by this table, everything is unknown. And everything is unknown means that those probabilities in this table are those parameters theta. All right? So the idea is how are you, there are 2 things, right? One is to estimate the static parameters theta. And those parameters theta don't increase as your data set increases. So for example, in the hidden Markov model, you can keep collecting data. This theta will remain the same, okay? And we will do those things later on. But the number of hidden variables increases the number of observation data set increases, okay? So in some sense, the hidden x's are treated differently from computing the unknown parameters theta in the model. Okay, so I don't know, I think I'm going to show you a slide or 2, and actually I'm surprised that this is, okay, I don't know why this thing came here, all right? It doesn't matter. I think actually it talks about evidence, but let me go to this slide then. So, let's fix the parameters theta. So let's say you know all the conditional distributions in your graph, so that's why you say conditioning on theta. So we know theta. In a real problems, you will not know what theta is, you have to compute, but you know theta. And you want, given some evidence, so these are the visible nodes. And visible nodes actually means, like in this graph, the darker nodes, all right? And then you want to say something about the values of the hidden nodes. So you want to compute the probability of x8 given x3 with fixed parameters. So effectively what you do is a simple calculation that you see in this equation. There is a marginalization that you have to do on the denominator, all right? This is a very important quantity. This is the evidence. This is basically tells you how probable are the data that you have observed, okay? So this is how you calculate the evidence. And in the numerator, you need the joint distribution of the hidden and the visible variables. But the way I can tell you, and it may be on a coming slide, that if you want to pose a separate problem and you say, how do we compute these parameters theta, effectively, you compute the parameters by maximizing the evidence, which is the denominator p of x3 given theta. All right? So, okay. We don't need this slide. Really has some fancy details. So this is actually, I mentioned that theta, if you want to compute it, you maximize the evidence. Don't pay attention to this term here, to the second. What have I done here? Before I had the probability of xv given theta. So here I wrote this. This is sort of my log evidence, the log likelihood, data likelihood. But I have done something else. The fact I wrote it as summation over n. So what is this summation, you think? Why I sum it? What is n? What's capital N? Huh? hidden layers? No hidden layers here. So usually when you do calculate the likelihood, right, you maximize the likelihood of the data. What is the assumption implicitly implied by writing like this? That my data are IID, okay? All right. So, so basically we find the theta that maximizes the log likelihood, and also to stabilize the problem, which is equivalent to computing a math estimate, I have added here the log of the prior of theta, right? So this likelihood times the prior, they give me the posterior of theta, okay? Hidden variables are not there, have been integrated out, okay? So maximizing this and performing this problem, you get your point parameters. And again, we will see this problem in detail with lots of numerical and analytical results later on in the course, but it's a good idea to know what it means computing the hidden variables in these parameters theta. Right? And another problem that maybe we will discuss in April, very close to the end of the semester, would be this problem that it goes under the name Notcelerity. So for example, in our sprinkler wet grass problem, let's say that on different dates, somebody does observations when it's cloudy, if the sprinkler is on, if it rains, if the grass is wet, and you collect a bunch of data, IID data. So maybe somebody will ask, if I have these observations, can you figure out for me what is the graph that represents these observations? In other ways, can you tell me that sprinkler depends on being cloudy or not, rain depends on that, wet grass depends on sprinkler and rain, etc. This problem effectively is posed as a structural learning problem, and think it as follows. Think that for every graph G, you can get the log likelihood of the data, all right? So the problem here is find the graph G that maximizes the log likelihood of the data, all right? So for each graph, like this graph, for example, you can go and calculate this, okay? And if you calculate, then for many graphs, you can say find me the graph that maximizes that. And this is sort of a penalty term to be sure that you don't have an overly complex graph. We discussed a little bit about these things in the fall of the balance of between fitting the data and complexity, right? So you don't want to overdo it. Again, we will come up to this problem in sometimes immediately. Okay, and I want to introduce one more fundamental concept that you may have to do some programming, and hopefully Suvik takes notes on this, that has to do with ancestral sampling, okay, because this is sort of very essential for, if you have a distribution over a graph and you want to take samples from that distribution, and there is a very efficient way of doing this. So you remember in directed graphs, right, the distribution was, let's say we have a chain, okay? So the probability of x1, x2, x3, xv is the probability of x1 times the probability of x2 given x1 times the probability of x3 given x2. Or in general, we have a product of the probability of xn given the parents of the node n. All right? So ancestral sampling, to take a sample of this variables x1 to, let's say, xk or xv, whatever how many variables we have, what you do is you start sampling first from the probability px1, you sample the root node, then you sample from the conditional of x2 given the parents of x2, and the parents of x2 basically is x1, which you already took a sample, right? And then the probability of x3 given the parents of x3, which I will assume are x1 and x2, right? So you basically proceed from the root to the leaves, sampling first from this marginal and then from these conditionals, and this is called ancestral sampling. And there's many algorithms in Monte Carlo methods that sort of take advantage of that. So in other ways, if a distribution is 50-dimensional, you don't sample in 50 dimensions. You sample from very low dimensional distributions by taking a factor, in effect, the factorization that the direct graph implies. Makes a bit of sense? Okay? All right. So let me finish from lecture 2 with another little concept that goes with the name Markov Blanket. Okay? So here's the idea. Markov Blanket is the set of nodes that renders a node P conditionally independent of all the other nodes in the graph. In other words, what is the minimal number of nodes that I need to know so that no information from any other node will make any difference in my, it's about saying something about, let's say, node P. So it's a set of nodes that make the node conditionally independent of all the other nodes in the graph. Okay? And so let me just tell you that what this consists of. It consists of the parents of the node, the children of the node, and the co-parents of the node. Right? Because some nodes have two parents, so the co-parents of the nodes. So can you tell me what is the Markov blanket of node 5? Huh? I don't hear. 2 and 3, no, the 2 and 3 are the parents. So you got me 1/3. What are the children of 5? 6 and 7. And what are the co-parents? What are the co-parents of 5? You notice 5 has a kid 7, and the kid has another father or mother 4. So 4 is a co-parent of node 5. Okay? Now, you may ask me, is there any proof of this? Where is this coming? And I'm going to at least highlight it in one slide to see this. But again, the Markov blanket of 5 are the parents, 2 and 3, all right? The children, 6 and 7, and then the co-parents, in this case, is 4. So basically, knowing 2, 3, 4, 6, and 7, node 5 is independent of node 1. Okay? So, in essence, think that these nodes isolate node 5, all right? They separate node 5 from the rest of the nodes in the graph, okay? And actually, this is indeed what this graph shows. Let's say this is, these are the parents, all right? These are the children, these are the co-parents. So knowing all this information separates, this is what's a blanket, it's it isolates X from the rest of the graph. An extremely important idea here, all right? So knowing parents, and again, everybody forgets that the co-parents come in the picture, okay? Like node 4 here, this is extremely important. So we did this example. So let me highlight the proof, okay? It's, a lot of these things they're obvious, but I want you to realize that they don't come from nowhere. There is some common sense derivation there. So let's say we want the probability, we want to know, given all the other nodes but node I, what's the probability of Xi? Right? Remember we said the Markov blanket is the set of the nodes that isolate node I from the rest of the nodes. So I want to know from what is this probability depends on. Here I put it basically Xi given all the other nodes. And what I'm asking is, do I really need all the other nodes, or some of those nodes basically will come to be unimportant? So what I have done is, I wrote this as the joint probability of all the nodes in the graph. Let's say I have M. And here I have the probability of this, of all the nodes but I. So I have to marginalize I out. So I use the factorization on the top, I use the factorization on the bottom, okay? And now I don't want you to read anything here, right? So don't get polluted by reading. Look at this ratio and figure out what terms, some terms are going to cancel from the numerator and denominator. What is going to be left there? So here I have the whole distribution, and there I have xi integrated out. So what is left? What are the common terms that will disappear so that this xi will make xi independent given this Markov blanket eventually? So what terms are disappearing from this ratio? Or even better, what nodes are they going to stay in that calculation? Is that mine? That's not very good. Okay. So there is an integration here of xi, right? So let's in this product there is a distribution of xi given the parents, right? There is distributions that involve the children given the parent xi, right? And those distributions involve also the co-parents. You see that? I mean, somehow here, because I'm integrating on xi, right, on the denominator, anything that relates to xi on the top has to stay there. And what distributions contain xi is the distribution of xi given its parents, all right? Nice, those two nodes. And then the distribution of the children of xi, and that depends also on the coparents. So these children depends on xi and the coparents. You see those are the only distributions that are going to stay? Yep. So basically this set of nodes that you see there are the Markov Blanket. Now so the Markov Blanket basically gives a very efficient way for computing the probability of a node given all the other nodes, all right? Because we said this probability only depends on the parents, co-parents, and children, okay? And I give you here one example of the probability of x5 given all the other, given all the nodes but 5, all right? You can write this, so if you use the factorization of the joint distribution, the only terms that stay is x5 given x2, x3, all right? 5 depends on the parents, children depending on 5 and 3, all right? And then notice what else I have. I have 7 depending on 5 and 6, the parents, and the coparent 4. Okay, so I indicated here for 5 stays in this calculation. Can you, well, it's written here. Again, those who have taken courses, for sure the computational statistics course with me in the fall will recognize basically this is the distribution you need to do Gibbs sampling, all right? So this is the distribution you need to do Gibbs sampling, and you see a nice factorization. So keep in mind this sort of ideas of ancestral sampling and the concept of Markov Blanket go hand to hand with a very nice implementation of Gibbs sampling. So we will sure give you homework on this soon. Okay, so let me summarize, and then we're done with lecture 2. Every node given the node descendants, okay? No, sorry, given the parents, P is independent of the node descendants, and excluding, of course, the parents. And the predecessors are a subset of the node descendants, so T is independent of the predescendants given the parents. And so this is called the directed local Markov property. This is called the order Markov property. You can appreciate why it's Paul ordered because, in essence, these nodes have numbering that is before the number of node P, right? We have a topological order. So this local property L immediately gives you the order Markov property because this is a subset of the node descendants. What is interesting is if this property is true, then also the other property is true. All right? And that takes a little bit of calculation. If you are interested, you can read this book for the derivation. So effectively, these two Markov properties, they are equivalent. And both of them can be shown that they are equivalent with the factorization that we have seen starting in lecture 1, basically, for directed graphs. So again, a local property, an order Markov property, and this factorization, you can prove from one of them, you can prove all the other ones, and the other way around. Remember, in some of the little examples we did, we started with this and we were proving those sort of identities, but also you can prove that starting with any of this, you can show that this factorization is true. All right. 110. I have to drink some coffee at lunchtime because my sister needs caffeine at this time, and without it, you may see me collapsing basically here. Okay. But one day I'm sure that you'll see all the coffee coming on the top of me, not paying attention, because talking and drinking coffee is not, they don't go hand to hand, you know. It's like drinking wine, right, and talking. All right, new topic. And this is going to be a little bit weird. It's not a new topic, it's basically a graphical way to figure out what independence relations you have in a graph, okay? So we don't really want to do heavy calculations, so algorithms that go under the name of DSeparation is what is going to allow us to figure out independence in the graph. So I have to admit, when you first see them, this may sound a little bit weird. The only thing I'm going to say, these are rules. If these rules are satisfied, and you can check that they're satisfied, then you can test independence relations. So these are not like something we derive. You come up with these rules and you can show that they're equivalent to these local Markov properties that we discussed before, and these rules go under the name DSeparation. So definitions. There is way too much information on the slide, so let's go line by line. An undirected path is disseparated by a set of nodes E. So E here implies the nodes that I know, that's the evidence. So an undirected graph is disseparated if at least one of the following holds. So in the various graphs that you see, this is my evidence. All right, this is my evidence. So here, the path from X to Z, all right, the arrows point in this way, but they can also point the opposite way. So it can be this or that. So in this case, we say that X and Z are disseparated from Y if Y is observed. Okay? So a lot of times, what you say basically is you look at this node and you see the arrow converging. This is heads and tails. So if you have heads and tails, or tail and heads the other way around, and this is an observed node, then X and Z are disseparated given Y. Okay? Disseparated, so we can start getting the concept, right? Means that X and Z are independent really given Y. Means that you cannot really reach Z from X by going through the evidence node Y. Okay? And this sort of little blocks that you see on the bottom, that's what they indicate, that somehow the path from X to Z is blocked if you observe Y. Okay? I'm throwing a lot of terminology there, but so this is one part of the definition. If you have this situation and Y is observed, okay, X and Z are disapparated from Y. Another case is when you have a fork situation, all right? So this is a parent pointing to two children. So again, P contains a fork, and Y is an evidence. X and Z then are disapparated by Y. So again, you notice the path is indicated here from X to Z is blocked because Y doesn't allow this to go through. So if you try to go from X to Z or from Z to X, the path is blocked. Haven't said what's the relation with independence or anything. I'm just giving some definitions, all right? But we can motivate what these definitions are going to be about, okay? So again, we will show that in this case, given Y, and having this fork structure with Y being in the evidence, X and Z are conditionally independent given Y. And then of course we have this explaining away situation where we have X and Z being the causes of the same Y, all right? So the arrows go like that. This is a V structure. And notice the definition suddenly changed. It says P contains a V structure like that. And we say that X and Z are disapparated if you have a V structure like that, and Y is not in the evidence. Y is not observed. So in other words, the path from X to Z is blocked if Y is not observed. Okay? Y is not observed. Okay? So basically, if Y is not observed, we will see in the coming slides that X and Z, are they? You remember when we did this example, what did we say for X and Z alone? What did we say? They were marginally independent, all right? So obviously, if this Y is not observed, I know nothing, X and Z are marginally independent. Once I observe Y, they become dependent. Okay? All right. So before we had only, X, Y, and Z nodes, but you can generalize this to a set of nodes. So if you have a set of nodes A, we say that in a given graph is disapparated from a set of nodes B, given some evidence on a set of nodes XC. If basically this set is disapparated from B given E. So if you try to basically go from any node to A to a node in B through the evidence nodes, that path is blocked. Okay? Using the rules that we have seen in the previous slide. So, this Bayes-Ball algorithm, right, is, the thing is, when you start putting this, topics in place, right, 20, 30 years ago when people were doing that, you can call anything, so the idea here is, I don't know the history, and I think it's very possible this is a reference in 1998 that introduced this concept of Bayes-Ball. So the idea here is to see graphically this separation. You throw a ball, and you try to see if a ball that you throw at X can reach Z, all right? And you have some rules that basically tells you when a ball can pass through an evidence node or node, okay? And so if you can reach Z, then basically the path is not blocked. If you cannot reach, the path is blocked and the nodes are independent given the evidence. So basically this is the same picture that we had before. But again, think you're throwing a ball, and it's important, I don't know if it says somewhere, the balls can travel opposite to the x directions. All right? And this has to do with the fact that, like in this case, the arrows can go the other direction as well, you get the same results. So the balls can travel opposite to the x directions. So here's a case, given y, if you throw a ball, it's blocked here, so x and z are separated. If y is not given, the ball can go through, you can go from x to z. Here, if y is given, this path from x, y, z is blocked, so you can, the ball's coming back. So x and z are independent, basically, given y. I'm just giving you this, because this is what we're going to use again. If y is not given, then the ball can go from x to z, no problem. And then this is the this explaining away situation. X and z, the path is blocked through y. If y is not observed, that's very important. If it's observed, then you can go from x to z. So if you remember those rules, basically you can test independence in any directed graph without doing any calculations by hand. Okay? Now, when I say you can do any calculations, obviously a good student will go and verify that actually they give you the right answers, right? So maybe I will do a trivial example, you guys can do a more complicated example. But before we do an example, I also need to tell you, this is the same slide, but you have to account for boundary conditions. So what happens if the ball reaches the root node or the leaves? And so there are two sets of boundary conditions. If you reach the leaf node and the leaf node is observed, the ball comes back, all right? If this is unobserved, basically the ball, you lost the ball, okay? Now, if the arrow goes in the other direction, okay? So in this case, if y is given, the path is blocked, all right? So the ball doesn't return back. It's the opposite of what you have here. And if y is unobserved, the ball comes back. Basically, you need something to have to stop the algorithm, right? And that something is this set of boundary conditions. So when we do some examples, remind me to come back on this slide 29, so you can see that these boundary conditions actually do make sense. Okay, so let me, so this is what we were talking on the previous slide, right? This is exactly this situation here. So if y is observed, the ball comes back. If y is unobserved, the ball is blocked. So let's consider the following situation. We have this V structure. Y is unobserved, all right? Don't pay attention to this. So y is unobserved. So if I throw a ball from x, what is going to happen here? If I throw a ball at x, in this case, will a ball go through? Huh? The answer is no. All right, this is blocked. Okay, so the path is blocked. However, let's consider the following case. Y is not observed, but let's say a children of y or some noisy representation of y is observed. Then what do you think happens? So only when we were looking at y, the ball was blocked, but now what you see in this diagram, what happens? And I mean, and I give you this concept, what about if y prime is a noisy version of y? Effectively, if y prime is a noisy version of y, observing y prime is the same as observing y, and when you observe y, what happens to the ball? You remember? So when you observe y, right, if you throw a ball from x, you can reach z, okay? So this is a tricky situation, all right? So you, when you have this V structure, this explaining away, and you have something, you have an observation, you have evidence on the children of y, treat them effectively the same as having observations on y itself, because basically this unblocks the path from x to z. All right, so let's try to prove this and see that this is not just rules, but somehow they do make sense. So let's start with the most trivial case. So we're going to take this, all right? So I'm writing my distribution P x and y and z as P of x, P of y given x, P of z given y, all right? So, all right? So we condition on y. So it means if I have evidence of y, what happens between x and z, and I'm just using, you know, on the numerator the probability of x, y, and z, on the denominator probability of y. This is P of x and y, so this is of P of x given y. So you notice that x and z become independent given y, all right? Okay, so when you have this node observed, and it's heads and tail here, heads and tail, and observed, then the path is blocked, and that's we call this graph separation, right? And it's equivalent to this independence relation that we see in this equation. So the idea here is, rather than having to prove an equation like that, if you can prove that the nodes x and z are graph separated, all right, and the orientation of the arrows here don't even make a big difference, okay? So if you use the biggest ball algorithm to throw something from x to z and that path is blocked, then x and z are independent given y, okay? So this is a nice algorithm to check this conditional independence relation. So can you know, this is the Markov chain, all right, first order, and it says, given xi, xi plus 1 is independent of all the previous xi's, all right, that's the first order Markov chain. Can you give me an argument of this being true using DSeparation? How are we going to establish that this is, you know, that they are DSeparated? So let's say in this case, x3 is the evidence, so my I is 3, and I say that basically what we need to prove is, let's say, that x4, all right, x4 is independent of x1. No, actually, you know, so this is the evidence, right? So we need to prove x4 is independent of x2 and x1. So how are you going to prove this? How are you going to prove that given x3 that x4 is independent of x2 without doing any calculations? But we need the algorithm, the biggest ball algorithm. So what situation do you have here with the arrows in this evidence node? This is what? Heads and tail, all right? So if you throw a ball, and node 3 is observed, what happens when you throw the ball from x3 to x4? The path is blocked, all right? So x4 is independent of x2. Similarly, if I throw a ball from x1, will it reach x3? I want to prove the independence of x4 from x1. So if I throw a ball from x1, will it reach x3? Yes, because this node is unobserved, but what will happen at x3? It will be blocked. Okay? So now this is a trivial example, right? And you take it for granted, but you know, if I start making fancy connections between the nodes, this is a very easy algorithm to prove independence without having to do any calculations by hand. And may I suggest to Suvik to give you a tough homework to work on these things, okay? So, right, to be sure, because this is sort of an important way of doing this. Okay. Again, so in this case with a V structure, right, we have tail and tail and observed. Okay. No, I'm sorry. It's not a V structure. This is the fork structure, right? So we have tail and observed. The path is blocked. All right. If it's unobserved, the path is unblocked. Okay. So in this case of the fork, given y and x and z are independent, if y is unobserved, x, you know, if in this case, you can see that the probability of X and Z marginally, basically, this is not equal to P of X times P of Z. So independence is not marginally true in this case. And again, this is the most difficult case. So if you have head-to-head, right, you have two causes of Y. If the path is blocked when Y is not observed, that's the opposite from all the previous cases. If Y is observed, then the ball can go through. All right. Okay. So again, goes to it's opposite from the other case. X and Z are marginally independent, but if you try to establish basically conditional independence, given the evidence Y, X is not conditionally independent of Z. Okay, and we talked about this. So, let's concentrate on this example, right? Don't read anything because, I have no idea what it says here, okay? Because we need to think together here so you can help me as it gets tiring speaking here. So in this case, I have nothing observed, and I throw a ball from X. Can you tell me what happens step by step? And maybe if you don't remember, we'll go back to all the previous slides. So I throw a ball from X, and I want to see what is going to happen to that ball. So what is my structure here is a V structure. All right. So this is unobserved. All right. So what happens to the ball? What happens to the path here when I look at the two arrows going down like that? Can I go from X to Y? No, because Z is unobserved. Can I go, however, from X to W? Can I go from X to W? Yeah, because this is heads and tail, this is unobserved, right? This path is not blocked. Okay? Then I reach W, and what happens to the ball in W when W is not observed? It goes out. So the ball is lost. It will never come back. Okay? Tell me now what happens when I observe W. So obviously, the ball in there, all right, we don't say anything. Similar situation. So the ball comes here. Okay. What happens? This is observed. From our boundary conditions, the ball comes back, and then this is unobserved. The ball goes to Y. So here, what can we say about X and Y given W? So do I have this? Is X and Y DSeparated? A ball from X can reach Y. So what can you tell me when W is observed? So a ball from X will reach Y, all right? So this is the reachability condition. So, so knowing W is more or less the same as knowing Z. And you remember from the V structure, knowing this, the evidence makes nodes X and Y what? Makes them dependent, right? Because anything you say about X or Y implies something about the other. Okay? All right. So here the tricky part is any information that you get down from children is basically propagates upwards, and this is the tricky part of this graphs. I know, but the idea here is why we're trying to see, we're not interested to go back from X to X, right? The idea is, we want to see if the ball can reach Y, if there is a path, not the path, a path, okay? All right. This is an example. You read it, you study it, it says the same things. And this is a very nice example from Bishop's book, actually, that does these calculations for this explaining away case, okay? So I am not going to go through all the algebra, and I believe I'm not sure, but I think one of their homework problems has this. Something like this, okay? So there is a homework problem, but so certainly do this homework, and when you see the algebra, you do the algebra. Don't say, yeah, I know he got 0.111. Get 0.111 because you will appreciate that this numbers is not magic, right? These numbers come basically by these conditional probabilities that we assume them known and these priors, okay? So when you do this algebra. So in this case, it's basically the same example that we were discussing with the rain case, all right? So knowing that this is 0, somehow saying something about B reduces the probability that this F is 0, all right? Since B explains the observation that I received from G. This is a very nice example. Please read it and do the calculations by hand. Can you show me with the biggest ball algorithm that A, given F, all right, that's my evidence, A is independent of B given F. Tell me what you will do with the biggest ball algorithm. So throw a ball and tell me all the rules. Can I reach? I mean, if this is true, right, means somehow the ball is blocked, right? So don't read, because when you read, you cannot think. It's like eating and driving, right? Or checking your phone when you walk, and then you expect me to pay attention to you, right? It's the same thing. So A independent of B given F. No, tell me about the ball. So I like the ball. So you throw a ball from A, what happens to it when it comes here? Can the ball go up to F? All right, so the ball here is blocked. Right? Right, because this is unobserved, okay? So this path is blocked, but anyways, even if that was not the case, and the ball goes up there because this is observed, this path will also be blocked, right? So you have no good luck there. Okay, this is sort of the same language or different words of exactly the same thing. Okay, these are all the rules. Now you may ask me why are the slides duplicate, because you know sometimes in year, let's say 2005, I write a slide and then I forgot, and then in year 2015 I prepare something else, and then you get these duplicate slides. But you know what? I like to keep them, because when you read them, yes, you print an extra page, but you may get something from a different slide that seems to be the same, but you may have something different there. Okay. Don't need this. So some simple examples just before we finish the lecture today, right? We already have seen this. So this is the, suppose you collect data from IID data, let's say from a Gaussian with some mean mu, or can be something else. Actually, this can be an indicator variable that tells you what Gaussian in a mixture you use. But the idea here is when you look at the probability of the data, so these are all the collections of data x1 to xn, each of these xi's given mu is independent. All right? So this is the IID assumption that you guys use in every statistics course you take. And the idea here is a representation, a graphical representation of the IID property is the simple graph that you see. So can somebody tell me just, why this graph basically embeds this independence relation? In other words, why x1 is independent of x2? What is the only way to go from x1 to x2 in this case? to go through mu, all right? So where do I get this? So don't get confused here, okay, because my x's are my data, obviously I have to mark them because that's my evidence, right? But when I write this relation, and I'm looking at this relation, my evidence, probabilistically speaking, is what variable? When I say P of D given mu, all right? So if I want to go from x1 to x2, I have to go through the evidence mu, all right? So I have to go to mu and then to x2. The path from mu is blocked, all right? Because I already know the values of mu, okay? So you need to start getting used to do these little graphs, basically, that they're not just sort of dummy graphical relations, but they embed probabilistic relations. So in essence, when you have this graph, immediately this is there, all right? So it's not one or the other. Once you plot it, this is what immediately you're implying, that you have the IID assumption, okay? And you can, obviously, you know here that if you marginalize mu out, all right, but marginally, basically, you can, P of D, it doesn't factorize as P of x1, P of x2, etc., okay? And so if there's no mu, all right, basically you cannot prove any independence. So let's do, so we can finish maybe one or two trivial examples. So let's prove this. All right, so we have evidence x2, and we want to prove that x4 is independent of x1 and x6. Okay, so x2 is our evidence, and we want to say x4 is independent of x1 and x6. So with the Vegas ball algorithm, what are we going to do? All right, so given x2, we need to prove that x4 is independent of x1 and x6. So let's start with x1 to prove the independence of x4 with x1. We're going to throw a ball, and the ball can go this way or can go the way like that. So if the ball goes this way, what happens here? Blocked. If the ball goes this way, can it go? Yes, yes, yes. Well, you tell me. What happens there? So can I go from x6, can I go to x2? So we can go? Okay. But remember, x6 is, the way that I see it, is a V structure. All right? So it's not observed. It's not observed, what means? If x6 is not observed, what happens? It's blocked, okay. And then from x6 to, to x2, is this path blocked here? All right, this is given, and then a ball can go this way, and then it's blocked at x2, so this is 2. So, if you try to do sort of this calculation with the factorization of the probability distribution, it will take you basically half an hour or something. If you trust these relations and you do them maybe once, twice, sort of you don't have to bother again, all right? And you can establish those for good. So let's finish with, so x1, given x2 and x3, x1 is independent of x6, okay? So, so x1 is independent of x6. There are two paths. One path is this way. Is this path blocked? Yes, right? Now, is this path blocked? Yes, done. All right. Here it says that given x1 and x6, x2 is not independent of x3. So given x1 and x6, so let's see, if we throw a ball like this, the ball can go through these tracks, and why? Because this is observed, then the ball can go there, can go to x3, then there is a path, so there's no independence. Okay? All right? So this is the biggest ball thing in action for a much more complicated problem. Okay? Let me just finish with 144. So I don't know what is my last slide, because I had, and we're going to come back on this. Come on. We're going to do the slides on Thursday, but I wanted basically to summarize the same slide I had before, where now in addition to this local and ordered Markov property, I also put this DSeparation property, okay, which is, sort of a graph theoretic way of separating a set of nodes, say, from B given some evidence. So let me just say, if I call this property, this global Markov property, call it G, this is the local directed Markov property, this is the order Markov property, and you can show that G leads to L, leads to O, and then you can actually show the opposite, which is not trivial, that O leads to L, leads to G. All of them are equivalent. Right? If you take one, you can drive the other two. Okay? And also you can show that all three basically lead to the same factorization of the joint distribution in the graph, which is the relation that you see on the bottom. Okay? So this sort of is something easy to remember. This is way more powerful basically, because in essence doesn't really even care what are the node descendants and what the direction of the arrows is, or what the numbering of the nodes is, right? So this DSeparation actually can be applied to both directed and undirected graphs, and it is the way to prove conditional independence to this. Again, if you want the proof of each of these, we already did this. We have shown them, at least with examples. The proof is really a few lines. And again, you can consult one of the Bibles in probabilistic graphical models for proof. Okay, 146, we will come back and finish some slides and then discuss about the elimination algorithm when we return on Thursday.